Good afternoon. Welcome back from lunch. Hopefully I didn't eat too much so you don't fall asleep, but we'll keep it exciting and interesting. Thanks for coming to the Earth on AWS session. We did one of these last year that was really well received, and so we wanted to come back and raise the bar a little bit. So we're really happy to have Kevin Murphy here from NASA to talk about what NASA's doing to encourage Earth science research in the cloud. So my name's Jed Sundwall. I run the Open Data program at Amazon Web Services, and what our program does is works to explore ways to share large-scale data in the cloud and help our customers, whether they're government agencies or research institutions that have large volumes of data that they want to share external to their organization, to figure out how to do that in the cloud. So before Kevin comes on stage, I just want to talk a little bit about our program and some of the experiments that we've done so far. So first of all, the question we do get from time to time is, why does AWS have an open data program? Why do we care about open data? And the short answer is that we care about open data because our customers really care about open data. We have a lot of customers, whether they're researchers or entrepreneurs or enterprises, that they rely on government data or otherwise publicly shared data for their missions. Their products would not exist without the availability of open data. And so what we get to talk to a lot of government customers who have data that they want to share is that when they make their data available on AWS, they're able to make it available to this large and growing group of users who really want to benefit from the data. And one of the benefits of the cloud is that it makes it a lot easier for people to work with data without having to acquire it and download it themselves. So there's a book that I highly recommend. It's a very quick read. It's called Data Driven. It was written by DJ Patil, who was the chief data scientist of the United States in the previous administration, and then Hillary Mason, who's a data scientist. They got together and wrote this book. It's actually free on the Kindle, so I make no money if anybody downloads it. There's no commissions on this one, but they finally wrote down this figure that gets thrown around a lot, which is that 80% of a data scientist's work is spent just preparing data for analysis. And whenever I talk to people about this and share this figure, everybody agrees. But if anything, when you're talking about working with Earth observation data or these like really heavy data sets that are terabyte or petabyte scale data sets, 80% is probably too generous, right? It probably takes more time than that to get those data into a place where they can be worked with. And we actually have a term for this kind of thing at AWS. It's undifferentiated heavy lifting. We talk about this all the time. And we think about undifferentiated heavy lifting in terms of what are the things that our customers have to do, what are the chores that they have to go through before they can actually start doing the work that differentiates them and that is actually related to their mission. So one way that we tend to think about what we do when we open up data on the cloud is that we can make free data cheaper. Right? So there's a lot of data that's free and the government makes it available for free, but it's just really expensive to get because it takes a lot of time to acquire, or previously, if you wanted to work with 10 terabytes of data, you needed to have 10 terabytes of your own storage to work with it. And so when data is available in the cloud, that's no longer the case. We did a project over the past few years with NOAA where we made a lot of radar data available in the cloud. And one of the really interesting findings from this experiment was that NOAA looked at the usage patterns of the data before and after the data was available in the cloud. And what you can see in this graph is about 4 years of data. It's actually a period of January to July from 2013 to 2016. And what you're seeing is access of NexRad radar data from NOAA's data centers. And in 2014, 2015, it was about 150 terabytes during that period of time. After the data was made available on AWS, usage skyrocketed 2.3%, or 2.3 times. And what we saw there, and then also most of the data actually just came out of S3 after they started making the data available on Amazon S3. And what this tells us is that there was a lot of latent research waiting to be done. There's a lot of work that people wanted to do with this data, but they weren't doing it because it was just hard for them to get. And we made it easier for them to access the data, and we made it possible for them to process the data in the cloud. It unlocked a lot of usage. And one surprising example of usage that we saw out of this was from a researcher at the University of Oklahoma who studies radar data to evaluate bird migration patterns. And so I'm going to go back and replay this thing. So these are birds migrating on a radar scan. So they actually have sort of a signature ring pattern that gets created as a flock rises. And what this researcher at the University of Oklahoma was trying to do was to find correlation or relationships between weather events, or things like droughts, floods, and other different seasonal changes and bird migration patterns. And he knew that the data existed in this NOAA radar data, but it was just really hard for him to get it. Acquiring the data from NOAA could take weeks for him to ship disks back and forth and find out who could get him the data. And now that the data is available on AWS, it's just a matter of seconds for him to make a request for the data that he wanted. And so that was a very unexpected application of this data that had been locked up before and that is now possible. And then another research thing that we've done is with Landsat on AWS, where we started making Landsat satellite imagery available on the cloud for anybody to use in the cloud. And what's been exciting about the Landsat data has been that we were able to work with a lot of customers who are really passionate about Landsat. They had really exciting things that they wanted to do with Landsat data, but it was hard for them to get. So we talked to them about how they actually acquire Landsat data. And actually, I'm going to go back a slide again. So Landsat data is provided in multiple files per scene. Like if you want to look at a part of the planet, Landsat data provides you with visible imagery, so data based on visible light, so you can just look at like a normal picture of that part of the planet, but they also provide infrared data, thermal data, and other things that people can use. And typically when you get Landsat data from a government server, you get it in a tar archive, so you just get one object per scene. So you get all the visible data, you get all the infrared data, and everything else. We talked to a lot of people, though, and we realized not everybody wants all of that data each time. And so they end up spending a lot of time downloading data that they don't even use. They just download it, they unpack that tar archive, and they throw away 60, 70% of what they got. So what we do with Landsat on AWS is that we get those tar archives from USGS. We use EC2 and Lambda. We have a workflow that we work on with Planet Labs that runs this with us. And then separate all the different files into separate files and make those available in S3. And what this does, it allows people to query precisely the data that they want when they want it. So they don't actually have to acquire or download any data that they don't need. And the response has been really great. We've logged over 1 billion requests for this data within the first year that we launched it. And the reaction to this has been really, really spectacular. But what we're really excited about when we do these things is when we can find evidence of people really saving time and developing new products because the data is available in this way. So I'll explain to you what this graph is showing you. This is from a guy named Drew Bollinger, who actually works across the street from the convention center. But he came up with this graph showing off the time required for him to work with Landsat data before and after Landsat on AWS. So those points that are on the left-hand side that are a little bit higher, that's how long it would take him to process a Landsat scene previously, just because of the time required to download the data and unpack it. And it's somewhere about 375 seconds, 400 seconds per scene that he was accessing and analyzing. Once the data was made available on AWS, that time per scene analysis dropped down to about 25, 30, 40 seconds. And there are about 90,000 points on this graph. And so I did the math, and what you're seeing here is about 250 days of time saved for one researcher. So that's 250 days of time back because he didn't have to spend time downloading data, that he could actually work on the analysis and finding insights from the data. And this is the kind of stuff that we love to see and shows us that there really is a lot of value to making data available in a cloud environment. So those are some of the experiments that we've done. It's a really fun project, that we get to work on with this open data program. But the real work is done by people like Kevin Murphy at NASA. And so that's why I'm really glad that he agreed to come speak to you about some of the remarkable stuff they're doing right now. Thanks.
Thanks, Jed. So it's great to be here today. We've been working with Amazon, I guess, in a number of different capacities for, 4 or 5 years. It takes a long time to get government systems into commercial cloud vendors. But I'm not alone. There are a lot of people in the audience today that really have made this possible. I shamelessly took a lot of their charts. So thank you, everybody. Do you have the clicker? Oh, sorry. I think I put it behind the platform. Oh, I see. All right, so at NASA, my job is to run the program which manages the Earth science data that comes from our Earth remote sensing satellites, aircraft, and field experiments. And as you might see it in the news or whatnot, we do have quite a few capabilities, many of which people actually don't know about. So I'm happy to talk here today. So what do? We actively manage NASA's Earth Science data within my program as a national asset. We got to keep it safe for the long period of time. We've got to make it available to researchers. We've got to document it precisely and fully so people understand what they're getting, because you want to make long-term climate records from this information, so that information needs to be preserved for a long period of time. We develop capabilities that are optimized to support rigorous science investigations, which can be different than simply looking at images or doing visual analysis of data. And we process, and more importantly, reprocess our instrument data to create high-quality records and long-term science Earth observation records. And that's really important, because if you're looking at something like temperature, if you're looking at something like land processes, you want to look at those on decadal scales, and to get the sensitivity of the measurement that you need to be able to be very rigorous in how you look at, how the satellite changed over time, how the aerosols changed, how all sorts of different things went into changing the observations that you see. So we've had an open data policy for a long time. The data that we have within NASA's Earth Science data systems are free and open to everyone for any purpose. It doesn't matter if you're from another country. It doesn't matter if you're commercial. It doesn't matter if you're a university professor. We've had this since 1994, and we continue to make sure that we apply this to all the new records that we collect. And I think we've been successful too in helping other agencies at other space agencies specifically make their data available. So what's our basic job? Our basic job is, as you can kind of see on the left-hand side over here, to take the data from multiple different platforms, capture and clean that information, process that data into higher level products, because it comes down as voltages in many instances from satellites, turn them into pictures or other understandable things, archive those, transform them, and distribute them to multiple users. And this is what we've been doing very successfully since about the year 2000 with the launch of one of the first EOS missions. And we make that available just about anybody. We do some basic services on these products. We make them discoverable through search catalogs. We've increasingly made them available through imagery and other mechanisms. But we're typically and principally a distribution shop at this point, right? So what we do is we take the information in, we put it out. And we do that for about 14 terabytes a day, about 1.5 million users. I think, or is it 2.5 million users, 1.5 billion products last year. So it's a lot of data, right? Our current archives are on the order of around 22 to 25 petabytes, and our growth rate is on the order of about 4 petabytes a year. How do we do this? The way we do this is through a variety of different processing and discipline-specific active archive centers or distribution endpoints, right? So if you look around, we got about 17 SIPs. We've got 12 distributed active archive centers. SIPs are the science investigator-led processing systems. They're the people that know how to process the instrument data into useful products for everyday use and research use. And then the DACs distribute those to this very large user community. And this kind of architecture has been in place for about 20 years, right? The number of DACs have changed. The number of SIPs have changed over that period of time. We've added more things. So it's a pretty resilient distributed archive and processing system. But we also need core services that tie those pieces together, right? So as all of these things kind of grew up individually, they have a lot of legacy in them, a lot of Fortran code, a lot of really interesting workflows. So we've built on top of them a layer of APIs and services that allow you to discover the data that's in each individual location, all 12 of those kind of things. Download that data and visualize that data for a vast majority of those projects. And we have clients that allow you to see them. So if we start at the top here, those are the DACs We've got 12 of those, and they have very specific tools sometimes for their communities. So we may have a cryosphere community that needs things in polar stereographic projections to look at ice caps, like Larsen ice shelf here. You have people that look at the atmosphere profile of aerosols, right? So where within the atmosphere do different constituents exist? Where does the dust go and come from, for instance? And those communities are somewhat smaller, but very important for our work. We then have open service APIs, which get populated by those data centers to allow people to search and discover the information that's at each individual one. And I'll go through some of these in a few minutes, but basically we have an image browse service, which is kind of like Google Earth updated every day with about 600 layers, right? We have a common metadata repository, which I'll go into in a little bit, which allows you to search through, I guess, close to 400 million records that we maintain at our DACs. Earth Data Login isn't really an open service API, but allows us to track who's using what and provide useful information, especially if we do reprocessing or other activities that are necessary. We monitor who uses it, obviously, and we have open source clients. One of the things that we did change in the past couple of years is that our development philosophy has really moved from kind of just open data to also open software. So everything that you see kind of in this kind of lower 2/3 here is all open today, right? And we do that in an open development framework and hopefully with Apache 2.0 licenses so other people can use them pretty easily. And this includes everything that I'll talk about in the future as well, all right? So what is a common metadata repository? It's fast, right? So it's our search engine basically. It allows us to do spatial and time searching. It's up, it's working in the cloud today actually. We moved this to Amazon like back in April, I guess, this year. It's standard compliant. It covers about 400 million files, like I said before, but it's prepared to go and accommodate growth in the future on billions of files and records. And we work a lot with the community to work with vocabularies and other keyword kind of standards within the scientific community so people can find the information that they need, right? And we work across organizations. So we have a lot of partnerships with the European Space Agency, within the Committee on Earth Observing Satellites. There are probably another 10 or 12 catalogs that link into this. We work with our partners at NOAA and USGS to try to make data available from all those different locations searchable, not only within this, but within their clients as well. So when we did our migration to AWS with our common metadata repository, we were able to achieve quite a good success rate on our target of less than 1 second searches, right? So you can imagine if you're doing like a spatial search capability, right? You're drawing a polygon over, I don't know, somewhere in Maryland, let's say, and you want to find all the data sets that we've ever collected that intersect with that specific location. It can be a little gnarly, right? There's a lot of stuff that you have to look through, and you got 300 million, right? And AWS really helped us do that. It supports 500,000 queries a day. It's supported by the CIO, so all that kind of stuff. But we see this as a real good success. We also have a search client, which was a lot easier to ask. I mean, it's just, it's not simple because we are in the government, but we were able to put it on AWS last September. So here are just 2 examples of these, and I'll go into a really quick kind of demo on this. On the upper left-hand corner is a previous version of our search client that allows you to kind of visualize and work with the data to determine what you want and select what you want to download. Some of our files can be incredibly large, right? If you look at some of the SAR files, they can be gigabytes in size, right? So for one area of, I don't know, maybe 150 kilometers by 150 kilometers, a couple gigabytes. Some of the Modus products, on the other hand, cover 2,000 kilometer swaths, and they're only a couple hundred megabytes, but they're still big, right? And in a single file, you may have multiple types of observations. So you saw Jed speak about multiple, like different parts of the electromagnetic spectrum, like visible, near infrared, that kind of stuff. Some of our files can have hundreds of different variables as layers within them. right? If you're looking at temperature profiles or something like that. The second thing I'm going to talk about, and I guess I didn't talk about too much in the previous slide, was that we have a GIBS API, or a Global Imagery Browse Service. And that allows you direct access to our tiling service, which allows you to see image representations of our data in very easy to understand and use formats. And the intention of our architecture is to have all of those APIs work together, right? Operate individually very well, but work together so people can discover the information that we want you to have access to. So let me get out of here real quick and show you some pictures. So here's the first. I thought this was, I don't know, I saw this tweeted yesterday, right, by DevSeed actually, which was fires in London on the west side as a result of that kind of apartment building yesterday evening, right? And you can see the 3 little dots. So it's kind of hard to see, but on the left-hand side of the L here, there are 3 dots. And so this is the capability that looked at this particular incident looks at pixels that are about 375 meters wide and tall. And you can detect a building burning if it's hot enough, any fire if it's hot enough. And we were able to do this within about 3 hours of observation, right? So this capability is just available for anybody to look at any time. So, you know, we not only service the research organizations, but we also service kind of application users, first responders, disaster types of activities. And you can zoom out over the world, and these are the detections of fire within those 375 meter squares around the world as of June 14th, maybe a couple hours ago. And you can go back in time, and you can look at it again. You can zoom in, you can zoom out. That's pretty cool, right? But I think the cooler part is this. You start to see the visual spectrums, right? So this is, let's see if I can figure out how to use a PC again. You can zoom in, and you can start detecting information underneath. And well, actually, it's always more fun to go to Egypt because it's always clear. Watch it not be clear today. Hold on. Yeah. Right, so you can start to zoom in and you can see, and you can go back in time. So you can see how things progress over time. And Worldview is a client, right? But there's this API that sits underneath of it that allows anyone in this room to hit the API and integrate the same imagery into their own clients or software. Now this is just one component of it though, right? So let me give you a little tour of Worldview. What does it do? So it has near real-time data in it. You can see at the bottom there's a time slider that allows you to go forward and backward in time. Each of the bars that's represented at the bottom, there's a blue one and some kind of grayed out ones, allow you to see what time ranges the data exist within Worldview for that period, because if you kind of go back in time, we don't have data back forever, right? Satellites get launched and they die. So you need to know when they work. So you can move around that. It's got the ability to add new layers. If you click here, you can go back and look at layers organized by hazards and disasters or by science disciplines, right? I can't remember how many there are in all, but maybe it's 400 or so. There's an events feature which we tie into some of RSS feeds or other events feeds, which allow you to go in and look at, tropical storms or other activities as they become available, both with our imagery and with the data. And you can go back in time with that too. One of the things that does is it selects the appropriate layers when you click on the correct disaster or hazard to be shown for that particular activity. You can, let's see, what else can you do? Let's add a layer that you can download data from. Oops. So let's say we want to look at aerosol optical depth, which is a measure of kind of how turbid, I guess, the air is. You can look through the descriptions of all the information and how they may be used. And you can select the different sensors because multiple sensors look at the same things, right? So this is a tool that allows you to look coincidentally at multiple different observations of the same thing from different satellites, which is really, really important for our researchers. But if you want to go here and download these products, you go this, and you kind of play whack-a-mole with these little pluses that are kind of hard to see up there right now. But we can change the color palette a little bit. Make it a little easier. And what this does, hold on, let me go back to data, is the data from Gibbs is populating the imagery, and these little boxes and orbit lines are coming from our common metadata repository. So this client kind of merges those two pieces. Another thing is if we kind of look, let's see, does that? It's not working. We can look at multiple types of progressions of information, right? So in this one, there's some theories that say that kind of dust storms from the Sahara that go into the Atlantic are the things that begin to generate like hurricanes and storm intensity, right? So with our AIRS instrument on our Aqua satellite, you can start to see, kind of if you look in the eastern Atlantic here, you can kind of start to see the detectable portion from AIRS with our MODIS instrument underneath of it as the background image. So the visible thing that you see there, with Africa is MODIS, and those little bright orange pixels are AIRS detections. And if you go forward in days, you can start to see the storm progressing, right? So typically you don't see these types of things. This isn't like, a rain cloud coming, but this is, a dust storm moving over the Atlantic. You can take a look at sea surface temperature, right? And in this instance, we have a modeled sea surface temperature, which assimilates sea surface measurements from multiple satellites and creates kind of this view, right? And you can kind of zoom in, and it makes a very nice gap-filled, cloud-free kind of image. And you can kind of see what it looks like. But you can compare that to the actual MODIS observations, which is an instrument on our Terra satellite, to get an idea of how well the model is performing versus reality, right? So if you zoom in, you can see that the MODIS observations are somewhat chunkier and they have gaps in them because you can't see through clouds with the spectrum, right? One of the really cool things that Ryan and his team kind of implemented recently is the ability to do like animations. So I'll do that real quick. And this is all kind of live. It doesn't get rendered until you call it. And we'll see how fast the internet is here, but maybe it's not fast enough. But you get the idea, right? You can watch the progression of things over time. And let me go back at this point to the presentation. But that gives you an idea of how you can explore information visually, right? There's a whole host of things in the world that you would never imagine. We've done a couple app challenges with these APIs, and people have developed apps to do fish clouds and posters and all sorts of crazy things. Cat clouds, was that? I don't remember what that one was. That was a cool one. So what has driven our growth, right? What drives our growth primarily is processing the data in new missions. So today we're seeing around, I guess this was back in December or something, but we had about 22 terabytes or 22 petabytes. We're much higher than that now. And how do we prepare for that in the future? Because things don't get smaller. We don't lose our responsibility to safely steward these products into the future. We need to make them available to people around the world without inhibitions on what they can use them for, right? But we've got some big problems looking forward because of the size of some of our missions. So we're obviously looking at AWS. We've been working with AWS for about 4 years, like I've been saying. And it took about 3 years to get NASA IP address space assigned to AWS, because there's a lot of security. But I think we've really kind of turned the corner in the past couple of years to do some really significant prototyping activities, which are probably going to impact how we work, right? And potentially even how people can work with us, much more along the lines of what Jed was showing earlier today. So we know we work well because we've had incredibly good American Consumer Satisfaction Index scores for a long time, right? So for 10, 15 years we've been doing this. We've scored higher than almost anybody in the federal government, but I guess that's not saying very much. But generally speaking, we've been doing very well. We get a lot of response rates back. But since we've been doing so well, we don't want to disturb what we've been doing. But we need to be able to evolve to allow people to use the incredible breadth of imagery and data that is coming from all these satellite sensors together, both not only from NASA, but from international partners and other agencies. So, yeah, can we afford it is always the big question. But so this is a very busy chart, but this gives you an idea of the scale of the problem that we're running into. Okay, so if you look on kind of the lower half of this chart, right? Everything kind of in bluish, white, or green is operating, right? Where NASA gets data or is operating as a primary mission or as an extended mission. Some of these missions have lasted 17 years. The first MODIS mission has lasted 17 years, which is just an incredible engineering feat. The things in kind of the yellow and orange are things that are in formulation or development. That means they're either bending the metal and making the pieces, right? Preparing for launch, or they're formulating the plans to do that, okay? And there's some really novel instruments on here. So, I mean, if you just look at Cygnus, what that does is it takes GPS signals in kind of a small sat constellation, and it can look through the eyes of hurricane walls to see storm intensity, measurements we've never been able to do before, right? That's a really strange thing. You're not going to find that in like an HD or whatever, a geotiff, right? That's a very hard measurement to make. And we have multiple instruments on the ISS, right, that take different sampling mechanisms. And I don't know if you know what the ISS progression orbit looks like, but it doesn't always have the same illumination or viewing geometries because of how it goes around the equator. You've got SMAP, which we're working closely with the Europeans on now because our primary radar, right, malfunctioned, but we can use data from our European colleagues' Sentinel-1 satellite and Sentinel-2 satellites to improve our soil moisture estimations, right? So there's a lot of ability that we need to be able to connect these things with. We have ISAT-2, which is basically an incredibly capable laser in space. It looks at how ice sheets lose mass over time. It can detect millimeter changes in the elevation of ice, right? Tempo, and then we get into the SWAT and NISAR, which are really the things that are going to change how we work. SWAT is surface, water, and ocean topology, right? That's a LiDAR, and some other capabilities which are going to look at like the volume of water in lakes and rivers, along with ocean like waves. And NISAR is a synthetic aperture radar that is being jointly developed by NASA and ISRO. And ISRO is the Indian Space Remote Sensing Organization, right? But the two of those together, I think, are going to account for about 30 to 40 terabits of data a day, right? And then we've got all these smaller things, so there's a lot of diversity here. So this is our archive, right? So you're here. Thank you, Katie. Now I know where I am. But you can see by the 2025 range, we're going to go from our whatever 25 terabyte or petabyte to close to 200 and some odd petabytes, right? That's our current estimate with our current capabilities. And as I said, our architecture is really, really tuned to do ingest, archive, distribution. We see, about a 1x, maybe 1.5x of our archive get volume distributed every year. Mostly the newer products, so it's probably like maybe 4x of whatever the current data that comes in goes out, right? If we have to distribute this every year, and we have to buy disks for everybody to process it, it becomes very expensive. But, as people like to remind me, this isn't our first rodeo. We had a bigger problem, at least from a slope perspective, back in the early 2000s with the launch of EOS Terra, right? But it took us a while to get that right. And what we don't want to do is take a while to get this one right. So, people always talk about bringing data close to compute, or at least they do in our circles. So we made a circle which shows, we got a large volume of data. We need scalable compute. We can't do that necessarily within a closed ecosystem, right? We can't do that in a government supercomputing lab necessarily, although those are still totally necessary and absolutely required. They're just not available to everybody, right? Because you got to get a NASA badge and provision, security checks, and all that stuff. We need to be able to do cloud native work in here to realize the benefits of this. We just can't forklift the stuff in. And we really see that having native computation, native cloud capabilities, the data, our services on top of that data in a minimal way, along with the open source components of it, will make it much, much more easily usable. That will allow us to invest research money potentially in the processing, analytics, and applications of those data without having to do that 80% of the work that we heard about earlier, which is kind of the data management aspects. So if you think of NASA's DAX as an incredibly well manicured and managed hard drive, right? That's what we'd like to put in the cloud, really. So obviously, there are some benefits for us, right? It could be cost effective. We're still testing this. So we appreciate all the effort that AWS has been helping us with that. We see that scalable performance is necessary, especially when we do reprocessing campaigns, right? When you have to reprocess 17 years of daily MODIS data at 500 meter pixel resolution globally, that can take 3 years right now, right? If we can exercise things like the spot market and other capabilities, maybe we can do that faster. We sure should be able to. Right now, when we develop our systems, we have not only, right, our production systems, but we have our dev, test, workload systems, right? So we're hoping to be able to spin those up and scale those down a little bit more. Deployment speed, we're hoping to improve along with the accessibility. Now, we obviously have some serious decision considerations for this. This is not something that we would go into lightly, right? We maintain the data that people use to do climate research. We maintain the data people use to look at how hazards and disasters are responded to and forecasted. Data that we have is used in like agricultural monitoring, right, around the world to do crop monitoring forecasts, those types of things. So we got to be able to afford it. We've got to be able to make it work within kind of the NASA security environment. We got to have a performance which allows us to be as good as we are today, if not better. And that's where we get into this operationally in the cloud thing, right? So we've got to be able to operationally work there. If we can, then then we'll probably make a big jump here. So how have we been kind of testing if we're going to do this? Well, we've done this in kind of small steps, right? We've done, like I said before, this Earth Data Search client already moved. We did that last September. We moved CMR, and we showed performance improvements in April. Our Gibbs system, which I showed before, which works on premise right now, is being migrated, and that's going to take a little more time because it's a bit more complex. And then we have two kind of core DAC function type of prototypes that are going on that can demonstrate if these systems will work. The first one is Cumulus, and I'll talk about that quite a bit, and then we'll talk a little bit about GRFN, or getting ready for NISAR. Cumulus is a prototyping DAX in the cloud. So this is a lightweight cloud-native framework for data ingest, archive, and management. And this is going to provide some of the core DAC functionality in a configurable manner. Or at least it's a prototype of that capability. So it does our data acquisition, ingest, metadata harvesting, and it enables each of our DACs, because we have an incredible bench of really talented scientific computing people at our DACs and disciplined computing people at our DACs, to try to get those folks to work together, right? But we also need to continue to support those DAC-specific customizations, like polar processes or special things for oceans or sea ice or what have you. The idea here is that we use product workflows, and I'm not going to get too much into the specific technology at this point, more of a conceptual component here, because we haven't determined what the precise best architecture is going to be. But the idea is that we have binned workflows, we have container image repositories for processing the products into higher level products, right? So the core processors to generate data from this level to that level, to generate the radiances to the clouds or what have you, right? We have our core metadata, metrics, and image repositories that interoperate together in this kind of vision document, right? So let's see, what do the different things look at, right? So the idea here is that we would have a code base available to all of the NASA DACs that they all contribute to, right? And this is open sourced. Hopefully now, I saw the message this morning that it had gotten through the Marshall process. And it allows for individual customizations and optimizations based on the science discipline needs, right? With some of the basic things that we all need to do taken care of by specialists. So how do you stage your data within the various storage tiers of Amazon to be most cost effective and to still help users? Do you go to Glacier IA? Do you go to S3, right? How do you make the hooks into our metric systems and image generation systems more uniform? How do you make the population of the metadata more seamless? While still allowing people to do the things that they need to do to have our users get the information that they need from our systems. Getting ready for NISAR, I kind of talked a little bit about this, but you'll see that kind of the orange portion there is processing. What we didn't really deal with too much in Cumulus, because it's just to manage our archives, is how do we process data once they're in there, right? You can imagine situations where instead of us generating all of our products all the time and storing them on disk, we generate some on demand to save storage space, or allow people to generate new ones. So NISAR really is a game-changing type of capability. It's day-night, it's all-weather. It's SAR, so it's difficult for most people to use. But it looks at earthquakes, it looks at carbon dynamics, it looks at ice, it looks at land cover, it looks at agriculture. It can look at, if you turn it on the right mode, you can see bridges sinking over time, right? Their foundations moving. It's an incredible instrument. The GRFN project will aid in how we deal with this amount of data, right? It's a collaboration between JPL, the Alaska Satellite Facility, and EOSDIS, which is based out of Goddard, NASA Goddard up here in Greenbelt. So it's leveraging AWS. It's leveraging this thing called the Science Data Segment, which is similar to a SIPS that I mentioned earlier. They're looking at how we do seamless data delivery and bulk reprocessing scenarios, how we optimize the storage of the level 0 data, right? So we don't have to have 2 copies of it, because that's typically what we do now. We have a copy at the science computing facility, and we have a copy at the distribution facility. And when you're talking about 200 petabytes, that gets expensive to back up twice. And we're engaging with the science community to work with some of these functions really, really early. Here's the architecture, at least a short-term version. We've got a landing bucket and all this stuff, but this is likely to change significantly over the next year, so I don't really want to spend that much time about it. But if you want the slides, I guess they're published, okay? And I am running out of time, and I want to leave a little time for questions. So in summary, we've been operational at EOSDIS for about 20 years, is that right? 1997, yeah. So in just the past 5 years, we've added 14 missions, so we're pretty resilient. But our future missions are really going to be big, and we got to start planning on how to work on those now so that we're prepared for them in their futures. The prototypes I just described are going to help us determine if we're going to make this jump into that kind of vision I described, right? We haven't said that we're going to move our whole systems in there at this point. We've got some decisions to make, some evaluations on the cost to conduct before we know that for sure. The vision, I think, looks promising. The implementation could be difficult. So we got a lot of work to do. And we're just happy that we were able to share this with you today. So thank you very much.
We have 1 minute for a question.
I'm sorry.
Go. All right, we got this guy. Well, I'll repeat the questions and speak, and then I'll repeat it.
Real quick. So 20 years ago, my first engineering job was actually to use aircraft company, helping to build the system and doing NASA. So I did not write the Fortran. I just want to say how proud I am of NASA and what they're doing for the community here. It's pretty amazing to see the resiliency. My question is, what do you see the biggest constraint now, right? So there's networking, there's compression, right? You're really pushing the envelope and you're moving it closer to the analyst desk. What do you see as the next hurdle that AWS or yourself is going to have to jump over to this system?
I think and this is almost a cop-out, but it's similar to the problems that we had previously, right? We have such a diversity of a diverse user community. Developing the tools that are ubiquitous across them is difficult, right? So teaching them how to use these new tools is not going to be easy, right? So we need to maintain what we do, but really kind of nudge them towards developing their software and algorithms closer to the compute, I think is going to be the biggest component, besides kind of our structural, like, organizational change.
Thank you very much.
Okay.
Thank you.